Development and characterization of 6-gap Bakelite multi-gap resistive plate chamber. Abstract. The multi-gap resistive plate chamber, abbreviated as MRPC, is an advanced form of resistive plate chamber, commonly known as RPC. In this detector, the gas gap is divided into multiple subgaps. These MRPCs are recognized for their excellent time resolution and high detection efficiency for charged particles. They have been successfully employed in various high-energy physics experiments such as ALICE at the LHC, STAR at ARXiv, and others at CERN, Geneva, Switzerland, and BNL, USA. Given their superior time resolution and cost-effectiveness, MRPCs can be a viable alternative to the more expensive scintillators currently used in positron emission tomography, PET, imaging. Typically, the MRPCs used today are developed with glass electrodes. However, in this study, the authors have developed a 6-gap MRPC using Bakelite electrodes. The outer electrodes have dimensions of 15 centimeters by 15 centimeters with a thickness of 0.3 centimeters, while the inner electrodes measure 14 centimeters by 14 centimeters with a thickness of 0.05 centimeters. Unlike the glass electrodes, these Bakelite electrodes are not treated with oils such as linseed oil or silicone for a smooth finish. The detector's performance was evaluated by measuring efficiency, noise rate, and time resolution using cosmic rays. This work is part of an effort to develop a prototype MRPC for use in positron emission tomography with time-of-flight TOF techniques. 1. Introduction. The multi-gap resistive plate chamber, or MRPC, was introduced in 1996 with the primary goal of significantly improving time resolution compared to the traditional single-gap resistive plate chamber, known as RPC. The design of an MRPC achieves this improvement without compromising other important characteristics, such as detection efficiency. In an MRPC, the gas gap of a single-gap RPC is subdivided into several smaller gaps by inserting thin, hundreds of micrometers thick, electrode plates inside the main gas gap. The high voltage, or HV, is applied only to the external surfaces of the top and bottom electrodes, while the intermediate electrodes are electrically floating. These electrodes are separated by very thin spacers, which determine the thickness of each gas gap. The readout panels, or electrodes, are located outside the stack and are well insulated from the high-voltage electrodes. The time resolution of a single-gap RPC is approximately 1 nanosecond, whereas the time resolution of an MRPC is significantly better. Figure 1 in the document illustrates a schematic diagram of an MRPC. A passing charged particle may create an avalanche in any one or more than one of the gas gaps. The avalanches in different gaps have the same time development. The intermediate plates are transparent to the avalanche signals, thus induced signals on the external anode and cathode are analog sums of avalanches in all gaps. The time jitter in the rise time of the signal is expected to reduce due to smaller subgaps, resulting in less jitter in timing. This causes much better time resolution than a single-gap RPC. From the simulation studies, it has been shown that the efficiency increases and time resolution improves with the increase in the number of gaps. If the gas gap of a single-gap RPC is divided into a number of gaps to form an MRPC, then it can be shown that the time resolution scales with the square root of the number of gaps. However, the efficiency does scale with the expected scaling law of 1 minus the quantity, 1 minus the efficiency of a single gap, raised to the power of n, where n is the number of gaps. The best time resolution obtained so far from MRPCs is approximately 15.8 picoseconds. Due to their excellent time resolution and detection efficiency of charged particles, several ongoing experiments like ALICE, STAR, as well as upcoming experiments like CBM will use these detectors for timing measurements. The MRPCs which are being used in the experiments are made up of glass. We have given an effort to develop MRPCs with Bakelite sheets. The major advantages of Bakelite over glass are as follows. 1. Bakelite RPCs can be easily operated in streamer mode, unlike glass RPCs, reducing the number of electronics channels used and hence the overall cost in an experiment. 2. Unlike glass, Bakelite sheets do not break easily as they have excellent mechanical strength. 3. Testing, handling, and shifting of Bakelite-based modules are much easier than the glass modules. The major disadvantages of Bakelite compared to glass are 1. The surface morphological structure of glass is smoother than Bakelite. 2. Glass electrodes do not sag when stacked one on the other in an MRPC. In the above-mentioned points, we have pointed out about RPCs instead of MRPCs as successful development and operation of Bakelite MRPCs have not been reported till date. Keeping in mind the major disadvantages of Bakelite over glass, we developed Bakelite MRPCs as these factors can be taken care of. The developed MRPC is a prototype and of small dimension, 15 centimeters by 15 centimeters, and placing suitable button spacers at suitable distances solved the sagging problem of the Bakelite. After several R&Ds, we succeeded in getting our hands on a suitable Bakelite sample which did not require any kind of oil treatment, unlike previously developed RPCs using Bakelite sheets while developing the detectors, hence ensuring a better surface morphological structure. The Bakelite MRPC was developed keeping in mind the potential application of MRPCs in medical physics, especially in positron emission tomography. It is a very well-known fact that MRPCs have very poor detection efficiency of photons at their optimized operating voltages for detecting charged particles. It has been observed that the photon detection efficiency of MRPCs increases as their operating voltage is increased. An increase in operating voltage leads to high gas gain mode or streamer mode of operation and reduces the number of electronics modules. Bakelite-based RPCs are very well known to be operated in streamer mode, hence our effort for the development of the Bakelite MRPC. 2. Development of 6-gap Bakelite MRPC. In this section, the development process of the MRPC is discussed. The MRPC was constructed using Bakelite sourced from the local Indian market. The specific details of the Bakelite used have been well documented in a reference study. The Bakelite plates, both inner and outer, were not treated with any oil. The outer electrodes had a thickness of 0.30 centimeters, while the inner electrodes were 0.05 centimeters thick. Table 1 provides a summary of the key details about the developed MRPC. Total area of the MRPC, approximately 15 centimeters by 15 centimeters. Active area of the MRPC, approximately 14 centimeters by 14 centimeters. Number of outer electrodes, 2. Number of inner electrodes, 5. Dimensions of the outer electrodes, approximately 15 centimeters by 15 centimeters with a thickness of 0.30 centimeters. Dimensions of the inner electrodes, approximately 14 centimeters by 14 centimeters with a thickness of 0.05 centimeters. Thickness of each button spacer, approximately 0.024 centimeters. Thickness of the side spacer frame, 0.40 centimeters. Total number of gas nozzles, 2. Total number of gas gaps, 6. Thickness of each gas gap, approximately 0.055 centimeters. As shown in Figure 2A, the side spacer was constructed from a 0.4 centimeters thick polycarbonate sheet, and 2 gas nozzles were properly attached to the frame to serve as the side spacer. The inner and outer dimensions of the frame are 14.5 centimeters and 15.5 centimeters, respectively. The same glue as referenced in the study was used in assembling the MRPC. The outer surfaces of the top and bottom electrodes were spray painted with a black, semiconductive paint mixed with a special dry thinner in a 1:1 ratio by volume. Both the paint and thinner were manufactured by Kansai Nerolac, India. 3. Cosmic ray test results. In this section, the test results of the MRPC are discussed, focusing on efficiency, noise rate, and time resolution measurements. These tests were conducted using cosmic rays at threshold values of 10 millivolts and 20 millivolts to the MRPC signals. The MRPC was tested with cosmic rays using 3 plastic scintillators, 2 paddle scintillators with dimensions of 20 centimeters by 8.5 centimeters, and 1 finger scintillator with dimensions of 7 centimeters by 1.5 centimeters. The overlap area between the scintillators was utilized to obtain the cosmic ray efficiency for a particular setup. The master trigger was generated from the coincidence of the 3 scintillator logic signals, with an average rate of approximately 0.008 Hz per square centimeter. The Camber Quad CFD 454 constant fraction discriminator, CFD, was used to digitize the signals from the scintillators and the MRPC. For timing measurements, a 16-channel Philips Scientific 7186 TDC module was used. A CAMAC-based data acquisition system was employed in the setup. The high-voltage module used was a CEN N471A, a 2-channel 8 kV power supply. Consequently, there was a limitation on the operating voltage that could be applied to the MRPC during the tests. HASHA 3.1 Efficiency and Noise Rate Measurements. The efficiency of the MRPC was measured using cosmic rays at two different negative threshold values applied to the analog signals of the detector, specifically at 10 millivolts and 20 millivolt thresholds. Figure 3 demonstrates the variation in the detector's efficiency as a function of the applied high voltage for both thresholds. The error bars in the figure are within the marker size. A plateau of more than 85% efficiency was observed for both threshold values. For the 10 millivolt threshold, the plateau began at approximately 15.2 kilovolts, whereas for the 20 millivolt threshold, the plateau started at around 15.8 kilovolts. This behavior aligns with the expectation that an increase in the threshold value leads to a later onset of the efficiency plateau. The noise rate of the detector was also measured as a function of the applied high voltage, as shown in Figure 4. For both threshold values, the noise rate exhibited nearly linear behavior. At 16 kilovolt, the noise rate at the 10 millivolt threshold was approximately 1.9 Hz per square centimeter, while at the 20 millivolt threshold, it was around 1.3 Hz per square centimeter. This trend reflects the expected behavior where a higher threshold generally results in a lower noise rate. 3.2 Time resolution measurements. The time resolution of the MRPC at different thresholds and applied voltages was measured. Initially, the time spectra were recorded for a sufficient duration and later fitted with a Gaussian function. The final RPC time resolution, denoted as sigma c, was extracted from the Gaussian fit after removing the contribution of the three scintillators. The time spectra of the MRPC were recorded at applied high voltages ranging from 15.4 kilovolts to 15.8 kilovolts across four different values. Figure 5 shows the variation of the time resolution of the MRPC as a function of the applied voltage at a signal threshold of 10 millivolts. As the figure demonstrates, the time resolution improves as the applied high voltage increases, with the best value of time resolution obtained being approximately 0.160 nanoseconds. For summary and outlook, we have successfully developed a 6-gap Bakelite MRPC. The detector was tested for its detection efficiency and noise rate with cosmic rays at two different thresholds, 10 millivolts and 20 millivolts, using a gas composition of 85% R134A and 15% isobutane, with a typical gas flow rate of approximately 0.21 liters per hour. The best efficiency achieved was greater than 85% at both thresholds. The efficiency plateau began at around 15.2 kilovolts for the 10 millivolt threshold and 15.8 kilovolts for the 20 millivolts threshold. The maximum noise rate measured was 1.9 Hz per square centimeter at the 10 millivolt threshold and 1.3 Hz per square centimeter at the 20 millivolt threshold at 16 kilovolts. The best scintillator corrected time resolution measured was around 160 picoseconds at 15.8 kilovolts and 10 millivolts threshold. For future work, the chamber will be tested with argon-based gas mixtures, and the R134A content of the gas mixture will be increased to reduce the optimized operating voltage. The detector needs to be characterized further for its photon detection efficiency. Additional research and development will focus on improving the time resolution and extending the efficiency plateau of the MRPC.